Okay, welcome to part 2 of today's discussion. Right before the break, we did this problem. Does everybody understand where the numbers come from, how to do this? These are the coefficients in front of each of the reactants and products. You need to always know it's products minus reactants. Now, but again, the equation is given to you on your equation sheet, so nothing has to be memorized. You just have to know how to use it. All the values will be given. Just like with delta H though, every once in a while they'll give you delta S and ask you to find the entropy of one of the reactants or products. And so you would do the exact same thing, except you would know this one, and one of these would be your X. All right? So it's pretty straightforward. Now, let's just look in your textbook. Okay? I need to unfreeze it. If we look at some of these other ones right here, on A, let's predict the sign of the entropy change. On A, just predict the sign. What's it going to be?
Decrease, negative.
Negative, because it's going to be 2 making 1. All right? So the sign is going to be negative. Here we have 1 making 2. So it's positive. But notice here, how many moles do we have here?
0.
0, because we only look at gas. It doesn't matter if it's a solid, liquid, or aqueous, we just ignore it. So it's 0 going to 0 plus 1. So it's going to be positive. All right, so these are easy multiple choice questions if you just make sure you understand that concept. You only look at moles of gaseous reactants or products. We just did this one. So if I look here, it's 1 plus 1 is 2, going to a solid.
It's decreasing.
It's decreasing, negative. Okay, a solid going to a 4 plus 3, gas, positive. Okay, now sometimes they say which one would be the most positive. Well, we would look then and say that's 0 to 3. This one up here was just 1 to 2. So this one is going to have a greater increase, a bigger value for entropy increase. They'll both be positive, but this one's just going to be a bigger magnitude, a bigger number. Are we all good with that? That's a simple, entropy type question. Let's see over here. All right, so if I look at number 33, and sorry, it's all curvy, but which of the following changes increase, decrease, or have no effect on the number of microstates? Okay, that's a fancy way. The more microstates, the more particles there are, the higher the entropy is. In other words, which one of these is going to increase the entropy? So if you see number of microstates available to a system, okay, what does temperature do? Well, how will temperature, if you increase the temperature of something, what's that going to do to the entropy of the system? Why?
Because it'll be more chaos.
Okay, MRY?
It'll just increase the chaos
What's it when you increase the temperature more, what's it increasing?
It increases the movement.
The movement, thank you, Omar. It's going to increase the movement of the molecules, and so more movement is going to be more chaos.
Yes.
Okay? So, a decrease in the volume. Okay, so if you just put it into a smaller volume, okay, what do we think? I mean, are we going to change the number of particles in there or anything? Not really. So it's really not going to have any effect at all. And a change of state from liquid to a gas is going to increase. Okay? What if I dissolve sugar into water? Does entropy increase or decrease? Okay? Let's just even say salt into water. What form is salt in the solid state? Ordered or random? Ordered. When I put it into water, these are going to dissociate from one another, get surrounded by the water molecules, and they just have total freedom, right? So what's happening to entropy? It increases. What about can of pop, you have the CO2 dissolved in water. CO2 gas dissolved in water. What happens to entropy as you put CO2 gas into water?
Decreasing.
It decreases because the gas is total freedom, but then you put it in the water, it's much more confined. Okay? So we need to be able to identify changes, you know, which one's gonna have a greater entropy or not, and just kind of go from there. All right, keeping on over here. Okay, so let's look at number 57. Let's see what you can do on 57. Just do it in your notes. feel free to talk with your neighbor and see if you got the same thing they got, if you have any questions about it. Are we all good? All right, so first off, given this information, okay, is the reaction endothermic or exothermic?
Exothermic.
And how do I know, Amar?
Because it's the negative.
Because that's negative.
Yeah.
Okay, that's your key. So I know that it's exothermic. Okay, so make sure that we know that right from the start. B, does the reaction lead to an increase or decrease in the randomness or disorder of the system? In other words, well, how does entropy change? Well, because it's negative again, that means it's going to decrease. Now, by the way, is this a favorable or an unfavorable change? The heat, energy, A. That's favorable. Okay, so that's driving. But this one is a decrease, okay, in delta S. Okay, so what does that change? Is that favorable or unfavorable? Unfavorable. So if this reaction is spontaneous, what's the only thing that can drive it? This would be an energy-driven reaction. Now, C says calculate delta G for this reaction. So delta G is equal to delta H minus T delta S. Okay, so delta H is negative 35.4 kilojoules minus, what is it at, what temperature? Standard, right? 298. But what I put in here for delta S? Yes, we have to convert it to kilojoules and make it here. So we have kilojoules here and kilojoules here. So it's going to be negative 0.0855 joules per K. Kilojoules per K. So now when you multiply by the K, it's just going to be kilojoules, so we can, the two will add together. But it's going to be a minus and a plus. So just for example, what do we get for this term? What is this times this equal, anybody? Positive what? 25.479. Okay, so that's just going to be kilojoules on that. So we can just see that this delta H term is bigger than the delta S term, which means the sign of delta G is still going to be negative. So that when you put all this together, delta G of the reaction is equal to, what is going to be, negative 9.92 kilojoules. So will the reaction be spontaneous or non-spontaneous? spontaneous or thermodynamically favorable. Okay? This is the most important thing, is changing that unit right there. That's where you're going to, I don't want to say you're going to make a mistake. Students in the past have forgotten to do that. They just kind of get going fast and they forget to look at units. Anytime you use this equation, I'm gonna say 99.999, there's gonna be a rare exception. They give you something in kilojoules, you don't have to change it. But you're gonna have to make your units match in this equation. Okay? So that's just a note to self, make a note in your notes, just, make sure to change, make the units the same. Now, you could have very easily made this joules and gone 35,400 joules and kept that one in joules. Then your answer would come out to be, 9,920 joules. And most of the time they say just use units, just as long as you say, if it doesn't specify. Any questions on that? So far we're kind of liking this, pretty straightforward. All right, so if we turn the page and look at question number 63. Oh, I need to unread. Okay, so you go ahead, just in your notes, answer number 63. Did anybody watch the slow motion video of thermite? Did I not post that in classroom? I know I posted it on YouTube. You guys need to watch that. I'll post it in the classroom, but I think I did. You guys need to go back and watch that video. It's really cool seeing it in slow mo. I'd like you already finished. And last time I was thinking about it, have y'all done the Google form as far as the AP Chemistry shirt? If you want it or not? If you don't want it, just don't fill it out, but if you want it, we're probably gonna make that order by the end of the week, so you need to do that. So first off, when it says combustion, what does that mean it's combining with? Okay, it means it's combining with oxygen, so it's going to be C8H18, and that is what is a liquid, plus oxygen gas, and it tells you that it's going to make CO2 and H2O. What state does it make the H2O a liquid? Okay, now we have to balance it. So we have 8 carbons, 18 hydrogens, so I'm going to put 9, make 18. Now that's going to give me 16 and 9 is 25. What times 2 is equal to 25? 12.5 or 25 halves. Now if you don't want to keep a fraction, you can just double everything. Okay? Just double everything, and we end up getting 2, 25, 16, and 18. Okay? So, 25 moles of gas, making 16 moles of gas. So what do you expect in terms of entropy? Delta S sign simply is going to be negative. What do you know though about combustion? What's delta H going to be? Endo or exothermic? Exo. Anytime anything burns, it's exothermic. You've never seen anything burn and it get cold. So if something's burning, you automatically know it's giving off heat, it's going to be exothermic. So delta H is negative. So notice they're both the same. So then it says, without using thermochemical data, predict whether delta G is more negative or less negative than delta H. Well, delta G is equal to delta H minus T delta S. So if this is a minus and this is a minus, doesn't matter what the temperature is, right? Do they even give a temperature? Well, they have delta G here, so I know it's going to be 298. Okay? So what's this term going to do? It's going to make delta G is negative, but is it going to become less negative, right? Because this is going to be a positive, so it's going to make delta H less negative. So again, you have to just put it in mathematically and just kind of work it out and just kind of see how it affects it. If these were both positive, okay, what's it going to make as far as delta H? Make it less positive, right, or more negative, or it's gonna make it be going closer to 0. All right. So that's just a theoretical question. Go down one, look at number 65. Classify each of the following reactions as one of the 4 possible types summarized. That's my, spontaneous at all temperatures, non-spontaneous at all temperatures, spontaneous at low temperatures only, spontaneous at high temperatures only. Okay? So, classify which one this is going to be. If I have a negative and a negative.
Spontaneous at low.
Say what I find?
Spontaneous at low.
Spontaneous at low. Okay? And again, you just plug it into this equation right here. If it's negative and a negative, that's really going to be a minus, minus, a minus, so it's really a minus and a plus. So as long as temperature is low, this term is going to be smaller than delta H. At some point you get this number smaller. But at some point temperature T, it's going to cross over. Okay? Some point temperature T, it's going to cross over, and this term is going to be bigger, and it'll become, so it's only spontaneous at low temperatures. Now here it's positive and negative. That one's easy. Is this a favorable change or an unfavorable change? Unfavorable. Is this a favorable or an unfavorable change? Unfavorable. So is anything driving this reaction? So what does that mean? Non-spontaneous at all temperatures, any temperature. Okay? And now we have positive and positive. So now if I have this being positive, that being positive, now it's the equivalent of a positive and a negative. So now increasing the temperature makes this become more negative. So what does that mean as far as the spontaneity? Spontaneous at high temperatures. So the only ones that are going to be temperature dependent is when the signs are the same. Two positives, two negatives. Maybe this will be easier. The two negatives, spontaneous at low temperatures. Minus, it kind of tells us like -0. Okay? Whereas positive and positive are only spontaneous at high temperatures. Positive, if it's positive and negative, it's never spontaneous. If it's negative and positive, it's always spontaneous. All right, now we go one more. Wish I could flatten that out, but I can't. Number 69. For a particular reaction, delta H equals -32, delta S -98. Assume that delta H and delta S do not vary. At what temperature will the reaction have delta G equal to 0? Let's see if you can figure that out. Everyone got it? Anybody need more time? All right, so when we're looking at this, again, they're asking for delta G, so delta G is gonna equal 0, is gonna equal delta H, negative 32 kilojoules, minus T delta, and we're looking, that's what we're looking for is T times, now notice again, it's joules and kilojoules, so I'm gonna change this to kilojoules, negative 0.098 kilojoules per K. Alright, so you always have to change that sign. So now the math is relatively easy. Bring this 32 kilojoules here is equal to negative T times negative 0.098. So then I divide by this negative and this negative are going to cancel out, right? Okay, so I'm just going to divide by the positive 0.098, so T is going to equal kilojoules per K. Kilojoules are going to cancel, K is going to come to the top, and what do we get as the temperature?
326 degrees Kelvin.
Say it one more time.
326 degrees.
326, okay? So that's the temperature in which the reaction, now notice again, it's negative and negative. It's only spontaneous at low temperatures. So if next part it says, if T is increased, okay? If T is increased, what's that gonna do to this term?
Increase.
Make it bigger. So it's gonna be minus and a plus, so as this gets bigger, we know that it's going to be spontaneous at the higher temperatures. Now, you can just remember that because we just talked about two negatives. It's gonna be spontaneous at low temperatures, okay? Oh, so that means it's gonna become non-spontaneous at the high temperature, okay? So this, as this term gets bigger, it's gonna make delta G become positive. Make sure I say it right. Make delta G become positive. So delta G means the reaction, positive delta G means the reaction become non-spontaneous. But again, if you just think about it from a theoretical point of view, two negatives means it's spontaneous at low temperature. That means an increase in temperature is gonna cause an increase, it's gonna cause it to become non-spontaneous. Are you guys getting all this? This is heavy duty. This is serious college chemistry going on right here. Okay? We're probably going deeper than you'll go when you take 101 or whatever in college. All right, one more. Not in the book. I don't think I gave this one to you. But this is baking soda. This is vinegar. Notice the positive thing's a hydrogen, so what type of compound is this?
Acid.
It's an acid. What do we know happens when you put acid into baking soda? It bubbles, right? Okay? And so we're gonna get sodium acetate aqueous, liquid water formed, and carbon dioxide gas. That's your bubbles that you're gonna see. All right, now, identify the reaction above as an acid-base precipitation reaction. Now, what would a precipitation reaction form?
A solid.
A precipitate, right? Okay, very deep. Is there a solid being formed there? No. Okay? Now, we haven't done redox reactions yet. We're going to do that, but this is not a redox. This is an acid. It's transferring the hydrogen to here to make H2CO3. So this is your acid, this is your base, and so it's an acid-base reaction, but that's the very last unit we do. Okay? But we identified the limiting reactant. We would have to convert grams of this to what? Moles divided by 1. How do we convert 0.875 molar to moles? Times the 0.0600 liters, right? You get moles divided by 1, whichever number is smallest in my limiting reactant. So we can do that, all right? I'm not going over those because that's not what we're talking about right now, but it is a review, you should know how to do that. C, the student observes that the bubbling is rapid at the beginning and gradually slows as the reaction continues. Explain this change in the reaction rate in terms of collisions. Now this is gonna be our very next unit of reaction rates, but why do you think it slows down?
Because it's harder for them to like interact with each other,
Because there's
like more products.
more products, there's less and less. So as the reaction proceeds, you have less and less reactants. The reactants have to collide with one another, and the fewer the molecules, the fewer the reactants. We're gonna find you increase the concentration, you increase the rate of a chemical reaction. So as the reactions proceed, they always slow down because the reactants get less and less and less concentrated. That's next unit, something to look forward to. Here's what we're gonna talk about. In thermodynamic terms, a reaction can be driven by enthalpy, entropy, or both. Considering that the flask gets cooler, so what does that make it? Endothermic, favorable or unfavorable? Unfavorable. What drives the chemical reaction between the baking soda and the beginner? Answer by drawing a circle around one below. So all you gotta do is draw the circle. So, is it an enthalpy driven reaction? No, because it's an unfavorable. What about our entropy change? Is it favorable or unfavorable? Favorable. So it's since we know it's not enthalpy, entropy has to be, so it's not gonna be both. Right? So this is, what year is this, 2018? 2016, okay? So this is a relatively new, this is just, they want you to just be able to understand that entropy driven, enthalpy driven, or both, or neither. Okay, just from a theoretical point of view. No math need to be done on that. Okay, so if the reaction gets cold, it's always endothermic, unfavorable. You want to look at production of gas for your entropy changes. Okay? Now, this is just because I love this question. Doesn't have anything to do with, justify your selection in terms of delta G. Also, you could do delta G there in terms of, delta G would be negative. Because, at room temperature, the temperature must be high enough to make that term bigger. I would use my delta H equals delta G is equal to delta H minus T delta S equation. Alright, but I like this one. HCl3 ion has 3 carbon to oxygen bonds. 2 of the carbon to oxygen bonds have the same length, and the 3rd carbon to oxygen bond is longer than the other 2. The hydrogen atom is bonded to one of the oxygens. In the box below, draw a Lewis electron dot diagram for the HCl3. Now notice they say diagrams. What would that intimate to you is happening, or what's possible?
What's it called? There are multiple ways.
So when there are multiple ways to draw the Lewis dot structure, what does that mean?
I forgot the name.
I finally heard it. Somebody said it, resonance.
Oh.
Okay? HCl3 minus, I have 1 plus 4 plus 18 plus 1, 22, 23, 24 electrons. They tell me I have carbon, oxygen, oxygen, oxygen. The hydrogen's attached to one of the oxygens. Okay? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. What's the problem?
Carbon.
Carbon's electron deficient, so what do we need to do?
Double bond.
With which oxygen?
The left or top.
Either this one or this one, right? So I can do this, and it's a minus, or I could do this. Because there's 2 possible ways of drawing this, that means there's resonance. Now, it doesn't ask anything about resonance, but that's why these 2 bonds are identical. These 2 carbon and oxygen bonds are identical. What's the bond order going to be? about 1.5. Okay, these still are going to be stronger than this. Okay, so it kind of described how you needed to draw this, but we should just be able to do it just if I knew that, draw it. But again, if you have more than one, if you can see resonance, draw all the structures. All right, good day. We've got a lot accomplished. We are completely finished with theory. We just got to put it all into practice.